Yeah. Partitions are finite sets of points. Okay. I've used the German black letter P there to indicate the family of partitions that are available for the interval AB. So italic P belonging to Gothic P there just means that italic P is a particular partition that belongs to the family of partitions, all of the interval AB. Okay? Another word for partition is division. Now, the norm of a partition is the length of the longest subintervals induced by the partition. So you look at all the little pieces that are created by partition points, you go find the largest one. That's the norm or mesh of the partition. Okay. It is controlling the mesh that allows us to take limits later. If we make the mesh get smaller for a given interval AB, what do you think happens to the number of partition points? Well, for a given length from A to B, if the partition norm is getting smaller and smaller, the only way to have that happen is to introduce more and more partition points, right? If you're chopping it ever finer. Same thing when you chop the vegetables, you just keep going, right? Dying little subintervals. Okay. So that's the way we're going to make limits happen, by forcing the norm to get smaller. Okay. There's the formula for the norm. The norm of a partition P is the max. Why the max and not the sup? Supremum. A supremum can deal with infinite sets of numbers. The supremum and the max are the same if you have a finite set, but they generally part company as soon as you have an infinite set. Okay. And since we only have finitely many subintervals, a max is good enough. So that's the formula for the norm of a general partition. Okay? Now, there's another way to capture the idea of a partition that's getting finer and finer, the mesh is getting smaller and smaller, the norm is getting smaller and smaller, and that's by ordering partitions. And it's done this way. Suppose I have an interval AB. And I have x1, x2, x3, x4, x5. So x equals A, x1, x2, x3, x4, x5, x6 equals B. All right, that's partition 1. Partition 2 might be that one, x1, x2, x3, x4, x5, x6, x7, x8, x9. Okay, so it has all of these, right, and more. The one that has more points but contains all of the points of the other one is said to refine the first one. So we would say that partition P2 refines partition P1. Or P2 as a set is a superset of P1. Right? Now, there could be a third partition of the same interval that has no points in common. We wouldn't say that P3 refines P1 or that P1 refines P3. They're not comparable, right? They're just different sets. However, there is a set, let's see if you can guess, there is a set that refines both P3 and P1. P1. P4. Yes, ma'am. Okay. And P4 is what? P1 and P3. So it automatically has everything in P1 and P3 in it. So it is comparable to P1 and P3 by set inclusion. From a set theoretic standpoint, it's bigger than either P1 or P3, even though P1 and P3 are not comparable. When I say not comparable, I mean in the order relation, you can't write the order either way, it just doesn't exist. So this relation of containment here, very often in terms of partitions, is written with this stylized, it's like a greater than or equal, but it's kind of a round greater than. I'm writing something that's looking like this. Okay? That means P2 refines P1. And if you stretch out all possible partitions, you have P1 and P3 here come together at P1 union P3, and P2 refine P1. Let's say that all the points in P2 are in P3 as well, so P2 is here, and there might be some more partitions, and every time we take their unions, we get something that looks like a feather, right? Even though these guys aren't comparable, they have always, because you can take the union of any of these two, they always have a common successor. There are no two partitions of the same interval that don't have a common successor, because all you have to do is unify them all. Whenever you have a situation like this, where you have a partial order, what's a partial order? A partial order is a relation. Let's be very specific. If I have a set X, partial order on X consists of a subset. It's a relation. So it consists of a subset of X cross X, such that these three things have to happen. XX is in it, right? Or that means if I use this as the partial order sign, it means X is less than or equal to X. Right? Yes. X, Y, and YX together being in the relation mean X is less than or equal to Y, and Y is less than or equal to X, which implies X equals Y. This is called anti-symmetry. This is called reflexivity. And the third one, I think Rob's going to tell us, right?
XY and
YC.
or XC.
And what's that? Transitivity. Transitivity. So unlike equality, which is reflexive, symmetric, and transitive, a partial order is reflexive, anti-symmetric, and transitive. Okay? So set inclusion is a partial order on sets, right? Partitions are sets, so there's this partial order from set inclusion exists for partitions. But we just saw that partitions, because you can unify into it, have an additional property, ultimate common successor property. Any two have one. If you pick P1 and P2, there exists a P3 such that P3 is beyond P1 or P2, right? It's comparable to either one and beyond both. The ultimate common successor. Whenever you have a partially ordered set with the ultimate common successor property, you are said to have a directed system. Okay, a directed system is usually indicated by D, and then the, I can write it either way, greater, this just means one on this side is the small one. A directed system. Okay? Now, for those of you that suffered through topology 2 years ago, did anybody do that?
That was a long time ago.